Welcome back, everyone. We are now looking at the experimental procedure for redox reactions, starting with part A1. So if you recall, in part A1, we're looking to react elemental magnesium with oxygen from air by heating a strip of magnesium ribbon in the flame of the Bunsen burner. So what I have here is a magnesium ribbon strip, which I am going to clean a little bit with a piece of sandpaper to remove any magnesium oxide that might be on the surface of the strip. Any metal that sits in air for a long period of time slowly reacts with oxygen at room temperature, and as a result it gets covered. I can show you, I have a strip that I have not cleaned, and you can see here it's a little opaque, sort of grayish color, and this one that I cleaned, hopefully you can see the difference. This one's lighter in color. I removed the dark gray layer of magnesium oxide from it. It's much lighter in color and shiny. I'm going to grasp this strip with my tongs. And remember, we're not trying to catch the ash because we're burning a small strip. In your procedure, it will say to try to catch the ash in hot water. We're not doing that, but I will explain what should happen if we did. But first, let's look at what happens when magnesium strip is placed in a, going to do one more because it's kind of fun reaction to watch. Clean the surface, as you can see, with sandpaper to expose metallic magnesium. And here is one more strip being burned. So as you can see, very bright light is being produced when magnesium is burned, and the resulting material is very brittle. It kind of falls apart right here, the part that's burned. It creates this ash-like whitish gray powder. So right over here is the equation that we already discussed, reaction of magnesium and oxygen. That happens when magnesium is heated, produces magnesium oxide. So if we did take the ash that contains magnesium oxide and we coated enough of it in hot water, magnesium oxide would have reacted with water. Oxides of active metals, when react with water, they produce hydroxides. So in this case, magnesium hydroxide would have been produced. And then magnesium hydroxide, because it has hydroxide ion in it, would dissociate in water and release hydroxide ion. You may recall that hydroxide is a sign of base. It's an essential base here. So if we did catch the ash containing magnesium hydroxide in water, it would have released hydroxide ions, which procedure then tells you to test the water with red litmus. You would see red litmus turning blue. Remember, blue basic. If red litmus turns blue, it indicates basic. So there will be a question on your post lab about what happened when water containing ash was tested with red litmus. You would say red litmus would turn blue because base would be produced, and base, of course, is magnesium hydroxide. So now we're going to take a look at part A2, and we're going to do this one in a hood. I already have everything prepared here. I'm going to turn on the light so you can see better. What you can see here is I have 3 test tubes that I pre-labeled. They're empty as of right now. One has 6 molar HCl, or will have 6 molar HCl. The other one will contain 6 molar nitric acid. And finally, the third one will contain concentrated nitric acid. I've got to put gloves on. Remember, all these acids are oxidizing agents, particularly concentrated nitric acid. I believe your procedure calls for about 1 milliliter of each acid, and to save time, I'm only going to measure approximate volume by measuring about 20 drops of each acid. So here I have 6 molar HCl, here I have 6 molar nitric acid, and here I have concentrated nitric acid. First, into each test tube, I'm going to put a piece of, I'm going to show it to you first. It's a piece of copper wire. So each test tube is going to get a piece of copper wire. They're about the same size. I did not measure or weigh them. We're not doing this quantitatively, we're just doing sort of observational type of work, so exact quantity of copper is not important. So we're going to start with 6 molar HCl, about 20 drops. 1, 2, 3, 4, 5, 6, 7, 8. So about 20 drops. I'm going to let it sit a little bit. We'll come back and take a look at it later. So next is going to be 6 molar nitric acid. Also about 20 drops of that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And finally this is going to be concentrated nitric acid. This one I'm going to be extremely careful with because this one is a very strong oxidizing agent. And hopefully you can already see the change. This one's definitely most obvious. Notice the color change of solution. Started as colorless, now it's gaining this green color, indicative of copper ions being produced. You will also notice the bottom portion of the test tube is gaining this brownish color, and this is the reason why we're doing this in the hood. That's because NO2 gas, nitrogen dioxide, the toxic gas I was talking about, is being produced. So you can clearly see the sign of reaction. So the products here are copper 2 nitrate, CuNO3 twice, and NO2 gas, which is hopefully visible as a brownish gas filling the test tube. This here is our 6 molar nitric acid. Probably not very much evidence of the brown gas, but there is evidence of reaction because solution is turning blue. And this indicates, of course, that copper nitrate is being formed. There is, of course, also NO2, but so little of it that we can't see it. Its concentration in the gaseous layer above the solution here is very, very small, so we can't see it. Although you might see a little bit of, now that I'm stirring it around, you might see a little bit of yellowish tint to the bottom of the test tube. I'm not sure if now you can, if you look at it. Compared to this of course is much more intense because this is concentrated and this here is only 6 molar. And you can see the copper is being dissolved. You can see bubbles in this one. That's NO2 gas forming. It's a very intense reaction here. Somewhat of a reaction here. Now you can hopefully see a little bit of brown, not as much as here, of course. And then this one here, I don't really see anything happening. The solution is remaining colorless and clear. Copper strip or copper wire is still shiny red, characteristic of copper color. So not much of a sign of a reaction in this one. And this one, of course, is HCl. So copper does not seem to be reacting with HCl. Remember, copper is an inactive metal. So is copper able to replace hydrogen from HCl? Doesn't appear so. But copper is being oxidized by both 6 molar nitric acid to a lesser degree and by concentrated nitric acid to a greater degree. You can definitely see there's a lot of brown gas in this one now. So that's that for this one, and we'll come back with part B.